Okay, we are going to try something here in episode 164 of the Rule Your Pool podcast. This concept today is larger than any one episode can hold, but I'm going to try to summarize it and cram it all into one episode. I can tell you right now, I'm going to have to overlook some details in the effort to simplify this. So, for the chemists listening to this, or metallurgists or material scientists, please understand I'm getting the general concept out here. I'm not trying to be super specific because every single metal is going to behave a little bit differently, and you know that. What we're going to talk about today is corrosion, corrosion of metals in particular. We've talked about oxidized metals before in previous episodes and in our blog, but today we're talking about corrosion, and we've all seen it. Looks like rust on things that have iron in it or steel. So if you've ever had a corroded heat exchanger and the metal starts flaking off, that's what we're talking about today. If you've ever been in an indoor pool, I know a lot of our listeners are operators of indoor commercial pools, and you see that metal starts to rust and it looks almost like it was spray painted on. We're going to talk about that today as well. It's a little bit over my head at the chemistry level. I'm more of a water chemistry guy, and I'm going to try my best to speak about metal chemistry. But I'm warning you right now, I am no expert. Thankfully, I found one. And when speaking with him, I learned a whole lot. So I'm going to try to do it justice and distill what he told me. And thankfully, he wrote it out in an email as well. We're going to do our best to understand corrosion. I hope that you don't fall asleep listening to this, Catherine. We're going to try to get through this episode together, understanding corrosion. I'm your host, Eric Knight with Orenda and Hasa. This is episode 164. Let's go. Welcome to Rule Your Pool, the podcast by Orenda that explains and simplifies pool chemistry so that anybody, regardless of experience, can understand it. I'm your host, Eric Knight, bringing clarity to these subjects so that you can bring clarity to your water. If you're ready to rule your pool, then let's go. Before I get into this, full credit is due to those who I spoke with. One guy in particular is a metallurgist and a material scientist. His name is Alex Wensley, and I appreciate Alex for writing out this detailed email after speaking with me. Very, very helpful because, like I said, I'm not a metallurgist. I'm not that comfortable with it. So I'm going to read some of the excerpts from this email and explain, and then put my commentary over it. So let's start with a definition. Corrosion is an electrochemical reaction. What does that mean? An electrochemical reaction means that electrons have to move for corrosion to occur. This is the same mechanism that makes batteries work. It's the same mechanism that makes electricity move. Electron transfer. When we talk about conductivity, we talk about ORP, all of these things are when electrons move. Oxidation, stealing of electrons. So you have two sides to any electron transfer. You have the anode, which is what gives up the electrons. And because it gives up the electrons, that's what would get oxidized in an oxidation reduction reaction. Okay? It is also, in this case, going to be the thing that gets corroded. If it loses electrons, it is what is going to become corroded. Almost all metals that you see in an indoor pool, stainless steel, iron, galvanized screws, anything that has rust on it, that's going to be the anode. The cathode is the oxidizer in an oxidation reaction. This is what catches the electrons. This is going to be whatever catalyzes that corrosion. It can be several things, such as another metal, chlorine, or specifically chlorides, sometimes even the ground, according to Alex. Anything that is taking the electrons is the cathode. Let's give an example relevant to swimming pools that you're probably all familiar with if you've been listening to this podcast. Let's talk about a salt chlorine generator. Okay, this is also electron transfer. It's not oxidation and it's not corrosion, hopefully. It's electrolysis, but it's still the transfer of electrons, so there's still an anode and a cathode. In a salt chlorine generator, the cathode side is going to have the hydroxide produced on it, and the anode side is where the chlorine is produced. And when the polarity reverses, meaning they switch, the electricity changes directions, that acidic chlorine gas is now on the cathode side, or what was the cathode side. And if you were to have scale form in there, we're talking about calcium flakes here, Now you've got this gas on that side that's acidic, and that's going to fracture off whatever calcification has happened on that plate. And that is what fractures that calcium off in flakes and blows into the pool. In an oxidation reduction reaction, also called a redox reaction, the oxidizer, usually something like chlorine or ozone or something like that, the oxidizer is going to steal electrons from the oxidant. Well, the oxidant is going to be the anode. The oxidizer, chlorine, is going to be the cathode because it's taking electrons. And those electrons have a negative charge. That negative charge reduces the valence of chlorine in this example, which reduces chlorine. It reduces hypochlorous acid down to hydrochloric acid because it's swapped an oxygen and it becomes chlorides, inert. It's no longer chlorine. So in my brain, and it's probably wrong, but it's a good way for me to visualize it and go into my left ear, come out my right ear, and it should make a little bit more sense. I think of conductivity, oxidation, electrolysis, and corrosion all as very similar things. One side's stealing the electrons, the other side's giving them up, and that's where we are. So it's pretty common in water that this is already happening. The question is it happening between metals that easily corrode? So let's get back to the notes that Alex sent me. There are different causes of corrosion in swimming pools. Yes, we talk a lot about the LSI, meaning the overall water balance. If you have aggressive water, meaning your LSI is red on the Orenda calculator, below minus 0.30, that can accelerate corrosion. But that itself is not the cause of that corrosion. It just makes corrosion a lot more likely to happen. The reason why is because you still need a cathode to steal things from the metal. We happen to know that aggressive water is directly correlated with corroding heat exchangers, for instance, or metal corrosion on rail goods, ladders, things like that. We see it all the time, but that doesn't mean it's the only cause. There are other things that can cause that, and you still need to have a cathode. But in a swimming pool, that cathode is usually chlorine, or more specifically, chlorides. And any chlorine product is going to put chlorides in the water. Any saltwater pool, you're putting salt in a pool, sodium chloride. It's the chlorides that get recharged during electrolysis in a salt cell that get recharged into active chlorine. In a bromine pool, it would be bromide that gets recharged by an oxidizer to become hypobromous acid. Those bromide ions don't go away. Same thing with chlorides. They don't go away. Chlorides also get into the air because nitrogen trichloride, also called trichloramine, is a byproduct of chlorine oxidizing a nitrogen compound. That gets into the air. And there are many different variations of these disinfection byproducts that go into the air. I'm very familiar with it. That rasp in my voice is from lung scarring. You probably already know my story, but I swam for a very long time, and I'm in this industry because of this problem. It's miserable to breathe this stuff in over time. And all this stuff gets into the air, and with an indoor pool in particular, all that moisture in the air is going to get dehumidified, which is what you want it to do. And that is going to condense on evaporator coils in the dehumidifier. Those evaporator coils, if they are not coated, they're going to get corroded real quick. I've seen it on literally hundreds of pools, photos and visits. But nowadays, they coat the inside of these dehumidifiers because where that evaporation occurs, the chloride concentrations are really high. And also, the pH is very low of this water vapor because we have tested the pH of the runoff moisture from an evaporator tray, and it was really low. It was like 2 pH. It was crazy. So much so that we have photos where the drip tray, like the moisture that runs out of the dehumidifier, runs down a sidewalk, and it's all exposed aggregate where the water runs compared to the rest of the sidewalk that doesn't have that water on it, which is perfectly fine. So we know it's very acidic, and it's coming out of the air, and that's because the chlorides are in the air. Not regular chlorides. They have to be in a form that can off gas, like nitrogen trichloride or various other disinfection byproducts. All this complexity in the water that bathers introduce, and God forbid you're using an algicide of some kind, when chlorine attacks those things, it can go into different forms, and those chlorides, a lot of them, can get into the air. Well, now they're in the moisture, in the air. Well, metal surfaces tend to be a little bit colder which means moisture tends to condense on those metal surfaces quicker. Think about taking a beer outside. When you have a cold beer and you go outside on a hot day, it starts to sweat. But obviously, that's not coming from inside the can or the bottle. That's coming from the moisture outside, hitting that cold surface and condensing immediately. That's why the outside of your beer gets wet, or any cold drink. It sweats, so to speak, but it's actually just moisture from the air because it's called the dew point, but it's condensing on that cold surface. The same thing happens on an indoor pool with metals. If you have metals, moisture will condense on those metals faster than it will condense on, say, tile or cement CMU block wall or a painted wall or drywall or whatever. Metals tend to have a lot more condensation on them. And so, indoor pool operators, when you see corrosion that looks like it's spotted, almost like it was spray painted on, that's telling you that there are chlorides in the air from the pool, off gassing, that condenses on those metals. And because there's chlorides in there, it's very corrosive. Boom. The pH of that moisture, once it condenses, is very low. That accelerates corrosion. We see this all the time. Anybody who's been in an indoor pool, if you're paying attention, look at metal fittings, look at screws, look at light fixtures, brackets, or anything holding up the duct or the ceiling itself. If things are not completely painted, coated, epoxied, etc., you're going to see a lot of rust in there. And think about it this way. If the air is doing that to steel, what is it doing to you? It's not good to breathe this stuff in. And there's tons of studies about it. But I'm going off on a rabbit trail. I need to get back on track. So according to this metallurgist I spoke with, these are his words, so I'm going to quote here. Chlorine can be incredibly aggressive to metals, as it has a very strong desire to pull electrons from metals and thus causing corrosion. The most common instance that I have seen chlorine corrosion is on ships at the beachfront communities, because the ocean is 3 to 3.5% salt, which makes it around 2% by weight with chlorine. I don't know what percentage the chlorine is in a common swimming pool, but 2% chlorine causes accelerated corrosion. There are entire labs devoted to salt spray testing for research on which materials can resist chlorine exposure the best. This is very important in beach communities for building materials for homes, buildings, etc. After viewing your photographs and after living in Florida for 6 years, I am certain the main cause of corrosion that you are seeing is chlorine being carried from the pool to those metal fixtures when the pool water evaporates. Pools are very humid environments, and everyone knows that water evaporates over time, but most people don't realize that small amounts of chlorine get carried in that water vapor. I have seen many instances of this, such as condominiums many miles away from the beach having their new outdoor railings rust within a few years. I have also seen it with businesses that have metal roofs just a few miles from the beach. They also rust within a few years. How about saltwater fish tanks causing fires in people's homes when the light fixture above the tank and its electrical terminals corrode from the chlorine exposure? These things happen. In all of these instances, chlorine was detected with spectroscopy. As an aside, I really need to learn how to say that word. I see it like electron spectroscopy. It's a type of study that you can determine materials. Anyway, the only way it could have gotten there was if it was carried in tiny droplets of water vapor. So you will definitely see accelerated corrosion of metals that are attached to blowers and HVAC units, as they will be moving a lot of air and therefore have a higher exposure to that corrosive water vapor. Okay. So he's basically reiterating what I just told you. I have it from personal experience and evaluating a ton of indoor pools over the last decade of my life. I've devoted my career to fixing this problem, and I've seen it personally. And there is a way to get this stuff out more rapidly, but there isn't really a way to stop it from coming out of the pool very effectively. You could do air stripping, source capture exhaust. You can do all sorts of stuff, but this process is going to happen one way or another. The question is, does it fester in the natatorium long enough to condense on the metals and cause this corrosion? Hopefully not. And you could do regular cleaning, which will help. But again, this corrosion is rampant in indoor pools. And unless you get the vapor out that contains the chlorides, it's going to continue. So then Alex continues and he says, let's talk about the metals that corrode heavily. Normal steel, cast iron, and copper. Now, most of these metals are not going to be able to survive chlorine exposure. I mean, think about copper getting oxidized so fast. It turns green, but it can also degrade. Think about your heat exchanger. This is why a lot of manufacturers have switched to Cooper nickel because it's a lot stronger, and that's good. But you can still minimize the exposure to corrosion by balancing your water and not overchlorinating your pool, and certainly not putting chlorine directly in your skimmer. Your chlorinator, if you have a salt system, should be after the heat exchanger, definitely not before. And you'd be surprised what we've seen out there. Some people put a trichlor feeder before a heater and they wonder why it lasts 90 days and then it's just destroyed. Pool pros listening to this will be like, oh gosh, who would ever do that? Well, somebody did because I've seen it. So, I'm glad you know it's wrong, but they didn't, or they didn't care. I don't know. Alex goes on to say that a lot of these metals, if they are present in an indoor pool or even around an outdoor pool or just exposed to chlorine in general, are going to be either epoxy coated or painted. And paint is a type of polymer which is non-conductive, therefore it prevents electron transfer, according to Alex. But once that paint chips or cracks or breaks open, the corrosion is not going to stop. Okay. It won't stop until the paint barrier is fixed. And he brings up this term called deleterious corrosion. Deleterious corrosion means that you're deleting material. That's the best way I can put it. What happens is this oxidation reaction creates an oxide of that metal, like iron oxide. That's a physically bigger molecule. So if you zoomed in with a really fancy microscope, you would see it is a bigger molecule and it flakes off because it can't stay bound to the metal. And so with friction or over time, just think of really rusted metal that's been sitting outside. You know how it just has those red or brown flakes that can break off? That's what I'm talking about. That's deleterious corrosion. And by the way, I've been in a pool myself that had a steel I-beam supporting the roof. They were about to condemn the building, by the way. It looked like a shark took a bite out of this thing. And we're talking about a steel structural I-beam, and it was literally missing probably 20% of the steel. It just corroded away in an indoor pool. It's just crazy what corrosion can do over time. And then you have more corrosion resistant metals. Now, they're not corrosion proof, but they are corrosion resistant, designed to handle chlorine a lot better. The main one is called stainless steel. Most of the rail goods you ever see in a pool, most of the fittings around lights, they're going to be stainless steel, either 304L or 316L. That tells you the amount of chromium in them. And I'm going to go back to reading directly from Alex because I don't want to screw this part up. So, direct quote from Alex. Stainless steels have chromium in them, which forms a chromium oxide outer layer, which protects the steel from rusting in normal oxygen environments. Timeout. Oxygen itself can oxidize metals. Look at the Statue of Liberty. Granted, there's seawater there too, and the ocean breeze and all that, but oxygen itself can turn a copper roof green. It's a lot slower because if you've ever been in a acid storage room, in a pump room, and it wasn't ventilated well, and there's some copper pipes for the heater or the boiler going somewhere else in the building, I've seen this a lot. Those copper pipes are green. That's because you've got all this stuff in the air. But let's get back to this. Normal oxygen environments. Chlorine is aggressive enough that it can attack that protective layer. So you have to use austenitic alloys. That's a vocab word. Austenitic alloys such as 304 and 316, which include nickel, and that offers additional protection. Alloy 316 specifically has molybdenum, which helps even more, and that's why 316L is commonly used in marine applications and swimming pools. That being said, even though they are resistant to corrosion, it depends on other factors such as the pH, because chromium oxide is only stable in pH ranges between 5 and 12.5. Anything more acidic than a 5 pH, and that chromium oxide layer will break down and not protect the stainless steel anymore, and it will corrode very quickly. All right, let's pause. This reminds me of two different jobs that I've been on. Indoor commercial pools, and the gutter was stainless steel 316L, perimeter overflow gutter. And we're talking a pretty big pool here, like a 50-meter Olympic pool indoor. Brand new. It's a multi-million-dollar facility, okay? Not a cheap pool, not a cheap building. And they had just done the plaster, and then they acid washed it. Think about that for a second. If the pH gets below a 5, stainless steel is going to corrode real quick. Well, guys, the fumes alone from acid are way below a 5 pH. And what do you think happened to that brand new gutter that they installed? It was destroyed. The process had begun. They didn't see it that day, but within 2 months, that entire gutter was orange. Brand new. These are the things that I've seen in the field. It happens. And it's really, really bad because once it starts, it's like Pringles. Once it pops, the fun don't stop. When you start the corrosion process and it's deleterious, you have to stop it. You have to seal it up so that no more oxygen or anything else corrosive can get to it and continue that process. It's really, really hard to stop corrosion once it starts. And there's a term called pacifying metal. I don't exactly know what it means, but in my brain, it means resealing that metal. Anyway, I could go down the rabbit hole more on commercial pools, but the majority of our almost 300 listeners are on residential pools. Whether you're a residential pool owner or a residential pool pro, let's bring it back to your world. I have seen some things in residential pools that surprise me. I have seen rust on handrails and ladders. I have seen rust on the ring around a light. I've seen black flakes on a saltwater pool. You know, everybody's used to white calcium flakes blowing through. What about black ones? You ever seen those? I have. Had customers send many pictures of them, and I'm going to explain what's going on there. Let's get back to the definition of corrosion. It is an electrochemical reaction. Essentially, electrons are being stolen from whatever's being corroded, where, in this case, the metal is losing electrons to the cathode. In exchange, an oxygen's usually going to go there, and you're going to create an oxide. Or whatever it is, it's going to be a bigger molecule, usually, and it's going to start flaking away or breaking off or whatever. This is deleterious corrosion. This is when things start to rust and break down. Thankfully, there's an answer to it because most of the materials that you're going to see in the pool business are already something like stainless steel, and they should be pacified, and they're pretty resistant. If you have your chemistry in line and you're not overchlorinating your pool, certainly not in high concentrations around those metals, you should be fine. But pools need to be constructed correctly too. Now, I am no expert on pool construction. I'll tell you that right now. I've never built a pool. I've been around to see some of it, but I've never done it myself. I can't speak to this, but I do know that it is unanimously agreed that when pools are constructed, all of the metal involved in that project has to be bonded. And bonding means you're tying it all together with enough of an electrical wire. I think it's a number 8 or something. Pool builders, please don't laugh at me. I really am not in your world. I'm a water guy. But you have to connect all the metal. So if you've got a light fixture and a railing and a ladder, but you also have a ton of rebar in your shotcrete, and then you've got electrical components on the equipment pad, like a pump and a heater and whatever else, all of that has to be tied together on a common bond. The reason for that is if you don't do that, there's going to be an electrical difference between anything that could create a stray current and that potential anode. So if a salt system, for instance, is creating chlorine using electrolysis, if you, for some reason, have some stray current leaving that salt system, and it happens, where's it going to go? Well, it can reach all the way through your plumbing out into the pool and find that unbonded piece of metal and take from it. It's called corrosion, electrochemical corrosion. Some people call it galvanic corrosion. Although Alex says galvanic corrosion, if you've heard of this, is actually using zinc. Zinc is an easier thing to corrode. It gives up electrons a lot easier. So if you've ever heard of something like a sacrificial anode, that's usually going to be zinc. And the reason is if you have stray current, if you have a cathode looking for electrons, it's going to be more attracted to zinc than steel, for instance. So galvanized things like galvanized screws or galvanized bolts or whatever, they are coated with zinc. And according to Alex, galvanized items like screws and fences are exactly this, a steel object coated in zinc, which makes the zinc corrode before the steel does. The galvanized screw lasts longer this way in corrosive conditions, but it will eventually corrode. It just takes a lot longer because the corrosion has to get through the zinc first. Timeout. I have a lot of experience in indoor pools dealing with corrosion. Galvanized is terrible in indoor pools. They corrode so fast. And here we are. It's because it's coated in zinc. Of course it's going to corrode. So you don't put galvanized stuff in a corrosive environment like an indoor pool. You don't put galvanized stuff in a pool environment in general, like a backyard pool pad. Don't do it, because that zinc coating is going to be very easy to corrode with chlorinated water. And then you're going to corrode the steel anyway. The process has already started. So why would you do it? Don't do it. You can use epoxy coated things though, which will minimize it. That being said, let's get back to this. I've seen things like an underwater pool light that just start rusting out of nowhere. Usually it wasn't bonded right. And so some stray current goes there, whether it's from the pump or whatever else. I'm not an electrical expert. I just know that when I've seen it, if it's like perfectly starting to turn orange at a slow rate, it's just like a perfectly uniform look, as opposed to one part of the ring is really dark orange and nothing else. That's usually going to be electrochemical. If there's a stray current somewhere, it's probably not on a common bond. One of the questions we get a lot of at Orenda is, what's the process to convert my pool from liquid or cal hypo to salt? Is there anything I need to be aware of if I'm going to convert my pool to a salt pool? Yes. If your pool was not constructed with a common bond, you're going to have some stray current possibly, and you're going to have a massive corrosion problem if that's the case. Now, most pools, if they're built to standards, are going to have a common bond. But there are a lot of pool builders out there, we hear about them every year, that cut corners. I mean, think about the ones that go out of business and then they don't show up again, and a homeowner's left with a hole in their yard. I mean, these things happen, and it's a stain on our industry. It's not good. But those kind of builders cut corners, and they may not do a common bond. And if your pool doesn't have a common bond, you could have a stray current issue, in which case, at a minimum, as a safety precaution, you should have a sacrificial anode, which is a zinc anode. Now, I don't know exactly where this should go. You should consult your manufacturers, equipment manufacturers, on how that should be installed. But I do know if you don't have one, I have seen black flakes in a saltwater pool. And here's what happened. It took some troubleshooting. And thankfully, we had people a lot more educated than I am on this that got involved to figure it out. They had a salt system. After the heater, everything was installed pretty well. But for some reason, there was a stray current, and it was going backwards against the water flow into the heater, and it was corroding the copper heat exchanger. And eventually, that copper flaked off, deleterious corrosion, and flowed through that salt cell, which then got oxidized by the high concentration of chlorine in there, and it turned into copper oxide that was so dark green, it looked black. It was blowing black flakes basically into the pool, just like white flakes of calcium would go in. They couldn't figure it out. They're like, gosh, is this an LSI issue? That's why they called us. Is it an LSI issue? I had no answer for it. I'd never seen it. And it just took somebody who knew what they were talking about. They're like, well, you need a sacrificial anode because there's a bonding gap. So if this has ever happened to you, I believe how they resolved it was they ran another bonding wire to everything just for good measure. And then they installed a sacrificial anode. And that sacrificial anode, I don't know exactly where it was installed, but I think it was between the salt cell and the heater. You would need to consult your equipment manufacturer because they're going to know electrical way better than I do. But they used that, and that stopped the problem. Because now that stray current either was fixed by the bonding wire, which could have been, I don't know, or it was as a safeguard going to the sacrificial anode instead of the heater. Now, I'd like to wrap this up with ways that you can fix corrosion and how you can prevent corrosion. This is going to go back to Alex. I'm going to read directly from him. And I quote, Eric, I don't want to be the doom and gloom guy, so I'll explain the most common ways to prevent corrosion mechanisms mentioned above. For crevice corrosion, the easiest way to prevent that is to prevent the chlorinated water from being trapped in the first place. So seal up the crevice and inhibit water from getting in there, and it shouldn't occur anymore. Yeah, I didn't mention this because he sent a very long email. Crevice corrosion, what we were referring to is if there's any micro fissure or crack in your plaster or gunite, chlorinated water can get into your gunite. For instance, if it's not shot to a minimum of 4,000 PSI, like WaterShape University says is the minimum, if chlorinated water gets to the rebar is just regular steel. It corrodes very easily. And as that corrosion expands, it can push through your concrete and your plaster and show orange lines. We've seen grid lines show up in plaster pools. Somehow water got in there. We don't know how, but it got in there. Chlorinated water did, corroded it, and over time, sure enough, it came out. That's what Alex is referring to with crevice corrosion. There was a crevice, water got through that crevice, got to the steel, boom, corrosion travels through concrete. Pretty crazy how that happens. But like you said, inhibit the water from getting in there. You could chip out the plaster, you could waterproof it, you could chip down to the rebar, epoxy coat it, and then patch it, then waterproof the surface. I mean, there's ways to do this, but you really just need to stop water from getting to that steel, and it should stop. Now I'm going to go back to his quote. For metals which are corroding in their current chlorine and pH exposure, including stainless steels, there are basically 4 choices. Number 1, select a more resistant metal such as titanium or nickel chromium molybdenum alloy like 316L stainless. Number 2, maintain non-conductive coatings such as epoxy, powder coating, or paints. As long as the coating does not crack or flake, it should protect the metal underneath. Number 3, cathodic protection via a sacrificial anode. We've already talked about this. Back to Alex. This is a solution used for boats, pipelines, and even residential water heaters. You strap a piece of zinc or sometimes aluminum to a piece of steel, and you give the chlorine something else to attack that is a juicier target. The anode, zinc, will eventually corrode, and you can replace it with another, but it keeps your steel protected because the steel is no longer giving up the electrons the sacrificial anode is. Galvanized items are exactly this. Number 4, cathodic protection via impressed current, ICCP. This is another solution used on boats and pipelines where you supply small amounts of DC current to the metal. In this instance, the chlorine grabs the electrons it needs from the electricity flowing through the metal, and the metal remains protected because it didn't have to give up its own electrons. This is not ideal in swimming pools, however, especially in a saltwater pool. Those electrons can go free, and we don't want to have electricity in our pool if we can help it. Anyway, he then goes on to be very humble and said, I want to preface my explanations above that I am no expert in analyzing corrosion mechanisms in swimming pools because I don't understand swimming pools well. I just know metals very well. Thanks, dude. You gave me a 5-page novel of information, and I really want to thank Alex again for this. This is very helpful. I hope this has helped you understand a little bit about corrosion, and I want to wrap it up with this. Low LSI is just one catalyst that can accelerate this, but by itself, it's not actually causing all of the corrosion. It happens to help corrosion because you're in a chlorinated pool. That's the real issue. You already have the chlorides. That's what's actually causing the corrosion, but lowering the LSI accelerates the conditions for that to happen. In fact, you can have a balanced LSI with a lower pH, and the lower pH can have more impact on the corrosion itself. So you can actually corrode a heater if you have acidic pH going through it, even though your pool is LSI balanced. Perfect example of this. Trichlor in a skimmer. Don't do it. Direct correlation from rotting out heat exchangers is getting a low pH through that system, and it happens one of 2 ways, or maybe both. Trichlor tabs in a skimmer, or column pouring acid, or just not diluting acid enough because it goes down to the bottom and it gets pulled into the main drain. Those 2 things will corrode your pool equipment faster than anything else that we've seen on a residential pool system. If you have electrochemical corrosion like galvanic or stray current or whatever, talk to your equipment manufacturer. I am certainly not an electrical expert. Talk to one of them, and hopefully they will be able to help you set up your equipment to prevent that further. All right, we got through it, team. We got through it. This has been something I've been pretty nervous about because I don't like getting out of my lane, but I know this is a very common problem that people have, and I hope this has helped you at least understand what you're up against so you can come up with some strategies. If you have questions, feel free to ask us. The email is podcast@orendatech.com, and we will probably put a blog together. I haven't actually started it yet. Thank you all so much for listening. This has been episode 164 of the Rule Your Pool podcast. I'm your host, Eric Knight with Orenda and Hasa. Take care.
Thank you for listening to Rule Your Pool, a podcast by Orenda Technologies. For more information on what we discussed in this week's episode, check the links in the description or visit www.orendatech.com.
I hope you find this show valuable enough that you tap that subscribe button and share it with your friends. You can also like us on Facebook and social media. And with our help, you'll be able to rule your pool without over-treating it with chemicals and wasting money. I'll see you next episode.